Hi everyone and welcome to another example video. Today we'll be seeing how to evaluate derivatives. In the previous lecture we saw one example where the derivative didn't exist, but for today's lecture we are going to consider some functions which are actually differentiable, that is you can find a derivative for them. So the first function we are going to consider is f of z is z cube, and we want to find df dz. So again we use our definition of the derivative in terms of the limit, that is df dz is just limit del z goes to 0 f of z plus del z minus f of z, and you have a del z. So let's put our function over here. Remember we are considering the function z cube, so just write it down. You have z plus del z cube over here minus z cube by del z, and in this kind of cases this del z is very small, right, and it also approaches 0. So anything of order del z square is negligible. Sorry, I shouldn't write it like that. So the way we write this is order del z square, these are negligible. So we just ignore them, we just take them to be 0 by default. So del z is 0, you write del z over here. This gives us z cube plus 3 z del z bar square, and then we have 3 del z plus, oh sorry, there should be a z over here, and finally you have del z cube minus z cube. Okay, it doesn't look really good over here, so let me choose another bigger space to write it down. So let's just cut it out from here. So we are now writing it down. And notice that we have said that this order of del z square should be taken to be 0, that is they are actually negligible. So these two terms over here, that is this guy, we take them out, and this guy we will take them out. So if we do that, and also notice that this z cube cancels with this z cube, because there's a minus over here and there's a plus over here. So what are we getting? We are just getting, oops, that's not a good color, yeah. So we are getting limit del z goes to 0, this is just del z, we have 3 del z z square and nothing else, and you can see that this is just this del z and this del z will cancel out. So as limit z goes to 0, the derivative, that is the thing that we are trying to evaluate, will just give us 3z square. So this result is a bit familiar from calculus of real variable. So if you generalize this, the result will be something like this, that is generalization. So let's say I have a function of f of z something like zn. So if you want to have df dz, this is just n into z n minus 1. This is how you can generalize it, and you can also compute the higher derivatives as well. So now we want to take a look at another function that is the derivative of the exponential function, and that will be important because the third example we are going to see today, we will use results from the derivative of an exponential function. So the second example that we will be considering today is that we have f of z is equals to e to the power I z, and we ask what is df by dz. The reason I'm putting this I over here will be evident pretty clear when we take a look at example 3. So at this point you might guess that df by dz should be something like this, right? But it's a guess and we need to prove it. Bear in mind that we are not taking any guarantee that this will be the case. It might be different, but let's try to work from the basic definition of the derivative and let's try to see what happens. So we write this df by dz, limit del z goes to 0, e to the power I z plus del z minus e to the power I z by del z. And what you can do now is you can take e to the power I z in common, or that is you can factor it out and then put this limit thing inside this curly braces. So this will be e to the power I del z minus 1 divided by del z. So at this point you might be tempted to use the power series of the exponential that you are familiar from real variable calculus, but note that for complex analysis we haven't introduced this power series yet. But a disclaimer is that even if you use the power series you will get the same result, but since we have not defined it yet, let's just try to work from the basic. So now we are faced with this thing over here, and one of the way to resolve them is again switching to Cartesian representation. So now we will switch to Cartesian representation, and if we do that, the Cartesian representation will give us df by dz is limit del x goes to 0, del y goes to 0. There will be this e to the power I z. I could have written it here, and note that this is something that is not changing, so that's why I haven't written it in terms of x and y's. So I just kept it in terms of z. I will only write the things that are changing in terms of x and y. So let's go and see. It was e to the power I del z, right? So instead of del z you will now have something like this. Let's put a third bracket over here so that we can distinguish e to the power I del x plus I del y, and there will be a minus sign in front of the 1, and this is just del x plus I del y. So now we have to choose a path. So let's write it in a side note that now we have to choose a path, and for simplicity I'm going to stick to del x equals to 0. This is the path I want to take, the path I want to take, and then I'll choose del y equals to 0 and see if they match. If they match, the limit exists, so the derivative will also exist. So let's try to see what happens when del x equals to 0. So when del x equals to 0, this implies df by dz is equals to limit del y goes to 0. We have our e to the power I z over here, and put curly braces here so that we can distinguish. This will be del x over, oh sorry, not del x, because we are taking del x to be 0, so we'll just put 0 over here instead of del x. So this will be just I del y, right? And here del x will be 0, and this I and this I will multiply, and that will be I square, which is just minus 1. Del x is 0, so you have e to the power minus del y minus 1. Now there is a nice thing about this expression over here, because you have exponential of a real variable, that is del y. So now you can use the power series. So again, write all these things down. Also you can take out this I outside, so let's do it. Let's enclose them with the first braces, and if I expand this power series, this is just 1 plus minus del y plus minus del y squared and so on, and there is a minus 1 at the last. So this dot 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 represents the other higher order terms in the exponential series, and it is divided by del y, right? And let's write this thing over here. So if you do this, this minus 1 and this 1 will cancel each other out. So let's mark them down. This one and this one cancels out. These two will produce a minus 1. So the first term will be minus 1. The second term will be plus del y. And the third term would be minus del y squared. Yeah, it should be minus del y squared because there is a minus del y cube that gives you a minus del y cube divided by y, so it's just a minus del y squared and higher order powers of this. And what was the limit we're considering? That limit del y goes to 0, right? So all of this will go away. So this is giving us minus e to the power iz by I, and my minus 1, that is this minus over here, is just minus 1, and it can be written as I squared. So it's I square e to the power iz divided by I is just I e to the power iz. But we got something, but this doesn't mean this is the final result. So now instead of taking del x to be 0, now let us take del y to be 0 and see if we get the same thing. So now we are taking del y equals to 0 case. So write these things again. So this time I'm just writing it directly to save some time. So when I do that, the denominator just reduces to del x, and for the nominator here we have this del y to be 0, right? So this will be just e to the power I del x. So this will be e to the power I del x minus 1, and note that we have not written the term e to the power iz. So this is just there because you can see from here that at first you have to take e to the power iz common, and then you can write it like this, and we are considering this del y to be 0 now. So this is just I del x minus 1, I del x minus 1. Now again you can use the power series, or what you can do is that you can use the representation e to the power I del x if you want to represent it in terms of sine and cosine theta. So let's try to do it. So cos theta I sine theta, right? There are two ways to do it. You can either use this representation, put it over there, and then what you need to do is that you need to use those theorems. For example, sin x limit x goes to 0 by x is just 1. So these are the type of things you need to use, but I won't go over there. I would rather stick to the series representation. And to do that, note that our variable is del x, it's a real variable, and I can be treated as a complex constant. So if I do it using my series representations, and note that now we are not writing this e to the power iz explicitly. So the first thing is to do is to evaluate this nominator. So let's try to do it. We're going to evaluate this expression, this expression first. So this expression will give us 1 plus I del x plus I del x squared and so on, minus 1, and it is divided by del x, right? So the only non-zero term will come from this part over here. So if you break it down more, you will see that this minus 1 and this minus 1, they are cancelling each other out. So let's cross them, and we have is I, then I squared. I'm not writing I squared equals to minus 1 explicitly now, because that won't be necessary, and the second term is just del x square, right? And the third term is I cube del x cube dot 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 dot, and this is divided by del x. Oh sorry, I have already divided by del x, so I shouldn't write that. So what is happening here is that, in case you are confused, is that there should be a 3 over here, because I am dividing, let me use another color, I am dividing this del x with the whole nominator thing. So when you divide this thing, that is this one, with this one, this del x gets cancelled out and the only remaining thing is just I. When you do this, this is just I square and del x square, and it will be just del x. So I have a term missing, so let me erase this whole thing and write it again. So the first term will be I, the second term will be I squared del x, third term will be I cube del x square, and so on. And let's put this expression, that is, let's call this expression A, and let's put this expression here, that is, put expression A over here. So we finally have limit del x goes to 0. We have our e to the power I z that is not affected by this limit operation, and we have I plus I square del x I cube del x square dot 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 dot. And you can see that only this term will survive, and all of this will just go away once you evaluate the limit, that is, you take x goes to 0. So we can say the result is e to the power I z times I. And you can see that in the previous case we also had this thing, I e to the power I z, and in this case the result is the same. So you can safely say that this is equals to I e to the power I z. And using this result, we want to finally prove something else, that is, we want to prove dd of z of sine z is equals to just cosine z. So recall that sine z is just e to the power I z minus e to the power minus I z divided by 2I. So again we will use the definition of limit. So limit del z goes to 0, and we have sine z plus del z minus sine z divided by del z. And this time we are not going to switch to Cartesian representation. The reason will be evident very soon. And let's take this 1 by del z out and write the signs into the exponential form. So the first one is just e to the power I z plus del z, oops, minus e to the power minus I z plus del z. This is the first part, and the second part is sine z, right? So let's try to write sine z, e to the power I z minus e to the power minus I z, and what we need to write down is 2I. There is another 2I, and if you combine them, the next line will be something like this: del z goes to 0. This is just 2I del z, and what we have here is that e to the power I z plus del z. Let's keep it that way because we are going to use a trick. And here you can see there is a term, let me highlight it, this term, and we are going to bring this term next to this term. So let's do it. There is a minus sign in front of it, I z, right? And there is a minus sign over here and a minus sign over here, and there is a minus sign over here. So this minus and this minus will give a plus. So you could have e to the power I, that is a plus sign in front, plus e to the power minus iz. So let me just write it down instead of saying it, so that you may understand better, that you have a minus sign in between, right? And you want to put these two terms together, mark with this green thing, these two terms together. So now what you have is, if I take a minus sign outside, we will have e to the power minus I z plus del z. And note that this minus and this minus should give us a plus sign, right? And I'm taking the minus sign out. So in general, it will have a minus sign over here, e to the power minus iz. And we are almost done. Now we can see that these two parts, that is part this one and this one, they have kind of decoupled, and we know that limit is a linear operator. So the next line can be written as follows: limit, okay, let me go down a bit, limit del z goes to 0, and we still want to, okay, so let's just put this 1 by 2i over here, and the reason I'll be explaining in a bit. And we know that limit is a linear operator, so put a big third bracket over here. First you want to do limit z goes to 0, and you want to write e to the power iz plus del z minus e to the power iz by del z. This is one term, and the other term is limit del z goes to 0, and you have a del z over here, and you have e to the power minus I z plus del z minus e to the power iz. Now notice that these are the expressions that we learned earlier. That is, this is just a derivative of e to the power iz, and this is a derivative of e to the power minus iz, right? So from here you can easily write, using the results from previous discussion, that this is nothing but e to the power iz, but there will be what? A I in front, right? And here in this case, oops, I have given a plus sign over here, there should be a minus sign, my mistake. It's a minus sign. And here you have a minus sign, and notice that there is, instead of I, like this expression, there is a minus I. So this minus I as a whole should come down. So you have this minus I and e to the power minus iz, and the rest of the algebra is easy. You just write I, 2i, and you have e to the power iz plus e to the power minus iz, and finally you could write e to the power iz plus e to the power minus iz divided by 2, which is nothing but cosine z. So finally we can conclude that d dz of sine z is cosine z, and similarly you can find d dz of cosine z as minus sine z, and so on. And the final thing I want to say for today, that the product rule and the division rule, in general the product rule, that is, if you have two complex functions, let's say f of z and g of z multiplied together, and you want to find out the derivative of this thing, it is true that the product rule will hold. If you take, for example, let's say I want to find sine z, cosine z, right? These are two functions that are multiplied with each other. So the first thing you need to do, you need to find the derivative of sine z. We have already found it before. That is, this is just cosine z. So the first term is just cosine z, and this leave this term alone. That is, it is equivalent to g of z. So this is cosine z, and the second term is leave the first term alone. That is f of z, which is just sine z, and the second one is the derivative of cosine, which is just minus sine z. So this is how you can easily use the product rule as well. So this will give you cos square z minus sine square z. So I hope the definitions are clear to you by now. This is how you can use the fundamental definitions to calculate these things. Even in the product rule, this is possible, but it makes the calculation really long. So whenever you have functions who are inside this product braces, that is the second braces, try to use the formula that you already know, and this will make life a lot easier rather than going for the formal approach of finding the limit where the del z goes to 0. So this will be it for today, and thank you.